Okay, so let's unpack this. Welcome back, everyone, to Beyond the Comfort Zone Talking Shit with KING-KAMBUF.
Hey there.
Today, we are doing a really, really special deep dive. We're getting into the brain trust of, well, integrated design.
We are.
We're focusing on the very first run of KING-KAMBUF's Design and Build School, or DBFK, and we're pulling directly from their edition 001 daily lecture and assignment.
Yeah, this is basically a master class in getting professionals up to speed fast. And you have to understand, this isn't just an architecture school.
No.
It's an integrated master's to PhD program. It's got architecture, civil engineering, urban planning, public administration, and construction management all mashed together.
And we are looking at day one, semester one, the very first studio, Studio I, and the title is Form Your Space Order to Code-Compliant Core.
That title really tells you everything, doesn't it?
Yeah, it's brutal in how clear it is. I mean, this is the complete opposite of that old idea where the architect designs some beautiful, sculpture
Right.
and then just sort of throws it over the wall to the engineers to figure out.
Exactly. The core idea here, the thesis, is that architecture is not just about a beautiful form. It has to be about encoding everything else. Structure, egress, daylight, cost, schedule, right from the very first line you draw.
From minute one, it forces the student to become what they call a builder-statesman.
A builder-statesman. I like that.
You can't just be an artist in an ivory tower. Every single line is either a financial asset or a legal liability.
Yeah, and so our goal for you, the listener, is to give you a shortcut. We want to help you understand how a master architect takes that pure, initial spatial logic, that concept, and turns it into something that's, actually ready for a building permit and a budget.
This is professional intelligence, basically, distilled down.
Yeah.
And the constraint, the one big challenge that governs the entire first year. It's just massive. And it drives every single thing we're going to talk about today.
It really does.
Students have to design a human-scale housing system that meets two goals that seem like they completely contradict each other.
Okay, what are they?
First, it has to cost less than or equal to $180 per square foot.
Wow. Okay, that's a hard number.
And second, it has to be adaptable and resilient enough for 50 years of use.
So that 180 per square foot number, that's physics. It's not a suggestion.
Not at all. It's the law of the land for this course. It dictates everything. What materials you use, how efficient your structure is, how complex your form can be.
To hit that target, you just have to be ruthless. Absolutely ruthless with your floor area in your structure.
And the 50-year part means you can't cheat. You can't hit that number by using cheap materials that will fall apart in 10 years.
Right, so that efficiency can't undermine the long-term durability or, the flexibility of the space. It has to perform ethically and financially for half a century.
So let's start where the course starts. This is from the first 30 minutes of the lecture. We're looking at the absolute foundational language, the building blocks you have to have in place before you even think about the building code.
Right, this is the first step. It's all about defining the architectural idea, but doing it with a kind of rigor that already anticipates the money and the law. And it starts with the parquet.
A power of the party.
The big idea, the organizing concept.
Yeah, the first 10 minutes are all about this. And a party, it's not the building itself, right? It's the diagram.
Exactly. It's the diagram. It's how you take a really complex program, apartments, stairs, elevators, trash rooms, and you boil it down into one single readable sketch.
We're talking about figure ground, solids, and voids, the paths people walk through.
And what's so critical here is they don't just teach one style. They show the elemental shapes, like the prime numbers of architecture. They sketch 3 of them live, the bar, the court, and the pinwheel.
Okay, let's break those down. The bar, that's the simplest, right? Just a long linear block.
It is. Super efficient for a site, great for density. But it has problems. The plans can get really deep.
Which means the middle gets dark.
The middle gets very dark. If you're designing what's called a double-loaded bar with units on both sides of a hallway, that center corridor is going to be dark and have no ventilation.
So you're immediately forced to rely on expensive mechanical systems?
And artificial lights.
Yeah.
And boom, there goes your 180 per square foot budget because your MEP costs mechanical, electrical, plumbing just went through the roof.
Okay, so then you've got the court scheme. This one wraps the building around a central open space.
An ancient typology. And it's really a low-tech performance move.
How so?
It immediately guarantees that almost every single unit can get light and air from 2 sides. the outside of the building and the inside courtyard.
So it breathes.
It breathes. The courtyard becomes this little microclimate, pushing daylight deep into the building. But, it's not perfect. It has its own risks.
Like what?
Well, security for one. Who controls that central space? And maintenance. Who cleans it? And acoustics. Sound just bounces around in a courtyard like crazy.
So your design choice has immediate social and operational costs baked right in.
That's it. It's all connected.
And the last one, the pinwheel. This one feels more complex. The units kind of spin out from a central core.
The pinwheel is great for maximizing corner units, which means more views and more light. It's also really structurally efficient for taller buildings because that central core acts as a shear wall.
What?
But it's geometrically a nightmare. Complex geometry means complex facades, more construction waste, higher labor costs to build it. It's a huge risk for that 180 per square foot budget.
So the lesson is that your abstract diagram has immediate real-world quantifiable consequences.
That's the whole point. And they drive it home right away by connecting it to a professional licensing exam question.
Oh, this is good. So they're teaching for the test and for the real world at the same time.
Exactly. They ask, which party bar, court, or pinwheel best supports natural cross-ventilation for units that are, say, 12 meters deep?
And the answer has to be the court, right? Because the bar would be a dark tunnel at that depth.
Unambiguously the court. A 12-meter deep unit in a double-loaded bar is basically impossible to ventilate naturally. The core scheme gives you two opposite walls with windows, so air can just flow right through.
So you get better comfort and performance without spending a dime on extra mechanical systems.
And that synthesis. Party equals ventilation equals cost savings.
Yeah.
That's the core lesson.
So the actual assignment for the students, the measurable goal, is to diagram their program into at least 3 different party schemes.
Yep. With clear ideas about circulation and where the core goes, it forces them to iterate, to test ideas quickly before they fall in love with one beautiful shape that just happens to be a budget killer.
It's about designing options.
Designing optionality, exactly.
Yeah. Okay, let's move on. The next layer of control, from about 10 to 20 minutes in the lecture, is proportion and order. So if the partner is the DNA, how do you impose order on it?
You use the grid.
The grid.
The grid is the blueprint for industrialized construction. It's all about using regulating lines, setting out your structure, and committing to modularity from the very beginning.
And I was really struck by the specific dimensions they give the students. Metric, 300, 600, 1200 millimeters. Imperial, 10 feet, 20 feet. These aren't just random numbers.
No, they're not suggestions. They are the constraints of the global supply chain.
Explain that.
Why 300, 600, 1200? Because drywall sheets, ceiling tiles, plywood panels, even bricks, they all come in standard sizes based on those modules.
So if your structural columns are aligned with the material sizes.
You minimize cutting, you minimize waste, and most importantly, you minimize the time it takes for someone to install it. And labor, you have to remember, is the #1 driver of cost overruns.
So a purely geometric choice on your drawing directly impacts capital expenditure, CapEx.
100%. If you choose, say, a 7-meter structural bay because it looks nice, you are actively designing waste and custom fabrication costs that will absolutely destroy your budget.
And this ties right back to what they call first cost sense, and another one of those professional exam questions.
Right. The prompt was, optimize the structural grid and the envelope spec to cut 8% of the CapEx without changing the gross floor area.
8% is a huge cut, just through disciplined geometry.
It is. And the answer is all in the structural bay. If a student picks a 6-meter grid, that's about 20 feet, that's the sweet spot for concrete or steel efficiency.
But if they go for a huge 12-meter bay to get those big, open, loft-like spaces,
the costs just skyrocket. The beams have to be deeper, the columns get bigger, the foundations get heavier. It's a cascade.
So the structural grid is the main control knob for the superstructure line item in your budget.
It's the primary optimizer. A simple, repeatable 6x6-meter grid keeps you on track for that 180 a square foot. Anything else introduces complexity, custom joints, and risk. Financial discipline is grid discipline.
Okay, so the third conceptual pillar from 20 to 30 minutes in is daylight first. This is about making sure the geometry you've chosen, the partie, and the grid also works for the people inside.
Right, this moves us from just structural stability to long-term human comfort and, crucially, operational cost savings.
This is where performance modeling comes in, right? Requiring light from 2 sides, using courtyards, thinking about how porous the facade is.
And they give a really critical rule of thumb here for sustainable design. It's called the thermal logic target.
Okay.
For a room to be considered naturally daylit, its depth must be less than or equal to 2.5 times the height of the window head.
Depth is less than or equal to 2.5 times the head height. Okay, so what does that mean in practice?
Well, imagine a pretty standard room with a 10-foot ceiling, so the top of the window is at maybe 9 feet. According to this rule, that room can only be about 22.5 feet deep if you want good, usable daylight at the back.
And if you go deeper,
The back half of the room becomes a cave. People have to turn on the lights, even in the middle of the day.
so if a student designs a unit that's, say, 35 feet deep, they've automatically failed the daylight goal for the project.
And they've increased the long-term operational costs, the OPEX. The design is no longer adaptable for 50 years because it's locked into a higher energy bill for its entire life.
It's a violation of the core mission.
Exactly. And they showed a simple sketch to solve this using a light shelf.
Right, tell us about the light shelf. It sounds technical, but it's a pretty simple idea.
It's a brilliant little piece of architecture, just a horizontal plane, usually above eye level on a window. It does two things. First, it blocks the high-angle summer sun, so it keeps the room from overheating.
Okay, that's shading.
Right. But more importantly, it acts like a mirror. It catches the light coming down from the sky and bounces it up onto the ceiling. And that diffuse light travels much deeper into the room.
So it basically stretches the daylit zone past that 2.5x limit.
It does, and it does it without you having to add more glass or expensive lighting systems. It's a perfect example of a simple, elegant architectural move solving a complex performance problem on a tight budget.
That's fascinating. So you start with a geometric rule, and then you tune it with a simple detail to make your floor plan more economically efficient.
And more pleasant to live in. It proves that those first design decisions are absolutely tied to the long-term financial health of the building.
Okay, so now we have to make the shift. We've got this ideal composition, good form, strong order, great performance. But the second half of the lecture is about crashing that ideal into the real world.
Yeah, this is where it gets real. This is about grounding the design in mandatory compliance and ruthless financial responsibility. It's the move from what looks good to what is required by law and by the bank.
The first step is mapping beauty to law, taking that beautiful party diagram and slapping a code overlay right on top of it.
And the number one priority is always egress, getting people out safely in a fire. If you fail on egress, your design is worthless. It doesn't matter how beautiful it is.
So the mandatory checks are the baseline things. What's the occupancy of each space? How many exits do you need? What's the travel distance?
And of course, ADA compliance, door clearances, turning circles.
Let's talk about the occupant load. They use a rule of thumb. 50 or more occupants triggers the need for 2 exits.
That's the designer's tripwire. Let's say your little housing module is really efficient, and you manage to fit enough people in there to hit an occupant load of 51.
Suddenly you need a second staircase.
A second remote staircase. And that immediately eats up a huge chunk of your floor area for something you can't rent out.
So your non-rentable space, the circulation, goes up, which means the cost per square foot for the rentable space also goes up, pushing you closer to that 180 cap.
It's a critical early decision. Do you intentionally keep the occupant load at 49 to avoid the cost of that second stair? Or do you embrace the density and find a really clever way to place it?
And that's the next test, isn't it? Another one of those IE-style questions.
Yep. If your travel distance, the length someone has to walk from the furthest corner of their apartment to the exit stair is too long, what's the best early intervention?
And the wrong answer, the superficial fix, is just to, add another door somewhere.
That never works. The best solution is a big strategic spatial move. You either split the core into 2 separate smaller cores, or you add an exterior exit stair.
Which is a fundamental change to the building's DNA.
It's a massive change.
Yeah.
But it's about strategic thinking, not just putting on a Band-Aid that will cause more problems later. The law has to define the bones of your building.
Okay, so the law sets the bones. Now the money comes in to dictate the skin. This next section is the cost encoder. First, cost sense.
This is where the architect has to put on their financial manager hat. The assignment is to produce a concept-level cost model.
And the guiding principle they teach is huge. Envelope before interior spend.
This is so important. Your envelope, the roof, the walls, the windows, that's your biggest fixed cost. It's the primary driver of your long-term performance, and it's the highest risk for budget blowouts.
So you focus your money there first because you can always argue about carpet versus polished concrete later.
Exactly. You can negotiate finishes. You can't easily renegotiate your wall system halfway through construction.
We'll break down the top 10 cost lines they have to quantify. This is a level of financial detail most students don't see until years into their career.
Right. These are the hard construction costs. You start from the ground up. Number one is substructure.
So foundations, the concrete slab.
Yep. And it's a huge risk because you never know what's in the soil until you start digging.
Number 2, superstructure, the frame of the building.
The columns, the beams, the floors. This is directly controlled by that grid choice we talked about earlier. Get the grid right, and you control this cost.
Then the performance shell. Number 3, envelope, and number 4, windows and doors.
These are your high-risk, high-variability items. The cost can change dramatically based on how much insulation you need or how good your windows have to be.
Then we move inside. Number 5 is interiors, and 6 is MEP rough-in.
Interiors. That's drywall, paint, flooring. Yeah. This is the most negotiable category. This is where you find savings if you're over budget.
And MEP is all the guts in the wall, the plumbing pipes, the electrical conduits, the ventilation ducts.
And that requires specialized engineering. So even at the concept stage, you have to have a solid placeholder budget for it.
Okay, then the outside stuff. 7 is site works and utilities, and 8 is fees and permits.
Site works covers paving, landscaping, hooking up to the city, water and sewer, and fees. Well, you got to pay the city to play. That's a fixed cost.
And finally, you have the builder's costs and the safety net. 9 is GC, OH&P, general contractor, overhead, and profit.
Right. The builder has to make money.
And number 10, the mandatory buffer. Contingency set at 10 to 15%.
And that contingency is key. Someone might ask, doesn't a 15% contingency automatically blow the $180 per square foot budget?
Yeah, that's a good question.
But the answer is no, because contingency is an allowance for risk. You have to budget for it. But the whole point of all this design discipline is to reduce your risk so much that you never have to spend it.
So the goal is to design a boring, predictable, buildable building so you can bring the project in under budget and keep the contingency.
That's the game. And that brings us back to another question. What is the single most cost-sensitive envelope element at this stage?
Given that 180 budget, it has to be the glass.
The glazing ratio and specification. Absolutely. Glass is expensive, the frame is expensive, the labor to install it is expensive, and it's a giant hole in your thermal envelope.
So if a student designs a cool-looking glass box with a 60% window-to-wall ratio...
They've just failed. They've blown the budget, and they've compromised the 50-year energy goal. The fastest way to save money and energy is to use less glass and make sure the glass you do use is really high quality.
Less glass, fewer problems. Okay, final part of the section. Tuning form for buildability and risk. This is where they really focus on pragmatism.
Yeah, it's about shifting from the ideal form to the optimized buildable form. And to do that, they have to create a risk register. They have to list the top 5 risks for this kind of project and, crucially, their mitigation strategies.
Let's run through them because this is basically a leadership checklist. Risk number 1, scope creep.
The silent budget killer, the mitigation. Assign brief and a formal change log. Even at this early stage, you get the client to sign off on the program. Any change after that gets tracked against time and cost.
It's just discipline. Risk number 2, egress noncompliance.
Mitigation, an early code check overlay. Basically, do the city's job for them. Find your own mistakes while they're still just lines on paper, because it saves you weeks of redesign later.
Risk number 3, envelope cost spikes.
The mitigation here is modular facade options. This goes back to the grid. If your facade is made of standard-size prefabricated panels, you reduce the time, waste, and risk of building it all on site.
Essential for hitting that budget. Risk 4, soil and service unknowns.
Mitigation, an early utility and geotech note.
Yeah.
You never, ever assume the site is clean. You put a note on your drawing to get a soil report and to locate all the underground utilities immediately. Proactive due diligence.
And the last one, risk number 5, community pushback.
Mitigation. Pre-engagement prompts. This is where the public administration side comes in. Community opposition can kill a project.
So you have to anticipate their concern.
You have to think about density, traffic, shadows. And you address those things in your design before you ever get to a public hearing.
This is a perfect transition then into the actual design challenge itself, the delivery.
Right. This section shows the insane rigor of the program. They're not looking for a pretty picture. They're looking for a fully integrated, rapidly deliverable product.
And the final exam for this lecture is the hands-on challenge. A 120-minute design sprint.
2 hours.
2 hours to design a micro-courtyard housing module, 6 to 12 units, that hits that 180 per square foot target.
It's a pressure cooker.
Yep.
That time constraint means you have no time for artistic exploration. You have to rely purely on the rules and the discipline from the lecture.
No design paralysis. You just have to go. So let's walk through the steps they have to follow. It's a model for efficiency.
Step 1. Program bubbles, 10 minutes.
Just analyzing the spaces you need. Units, circulation, services, but also the boring stuff.
The necessary stuff. Trash, bike storage. If you forget the trash room, your building doesn't work. The design is incomplete.
Step 2. Party times 3. 20 minutes. This is where you test your options. Bar, courtyard, pinwheel.
And this is the 20 minutes where you lock in like 80% of your building's entire performance and efficiency. It's the most important step.
Step 3. Massing and grid. 25 minutes. You commit. You pick your party. You pick your 6x6 meter structural bay. The column lines go down.
And at that moment, your design becomes financially accountable. The big money decisions are made.
Step 4. Daylight section. 15 minutes. You apply the window-to-wall ratios. You check that 2.5 times head height rule.
This is your performance check. And if your massing fails the daylight test, you have to go back and fix it, and the clock is ticking.
Step 5. Code overlay. 20 minutes. This is where you draw the law onto your plan. Fire separations, exit paths.
You literally have to draw the travel distance line and measure it to prove it complies.
And this is where they flag a really specific detail that can trip people up.
Right.
The ADA turning radius at unit entries.
A perfect example of a tiny detail with huge consequences. A wheelchair turning circle is about 5 feet in diameter.
So that dictates the size of the hallway right inside the apartment door.
It does. And if you forget to account for that space, your non-compliant little hallway forces you to move a wall. And moving that wall might mean moving a column, which affects every single unit above and below it.
It's a chain reaction, all from forgetting a 5-foot circle.
Compliance is spatial. It takes up real room.
The last 2 steps are basically a mad dash. 15 minutes for the mini cost and schedule, and 15 minutes to lay out the final board.
Pure speed and synthesis. And let's talk about the non-negotiables they have to show on that board. The code, performance, and schedule targets.
On the code side, they have to list the occupancy type, the construction type, and show placeholders for things like fire-rated shafts.
And on the performance side, they add another critical target beyond daylight, the acoustic target.
Right. Bedrooms have to be less than or equal to 35 dBA, which is pretty quiet.
It's quiet. And achieving that in a dense apartment building is really hard. It forces you to think about the walls between units.
You can't just use standard drywall.
No, you have to specify thicker walls, maybe double layers of gypsum board, maybe resilient channels to stop vibration. These are material choices that add cost to your interiors line item.
But they're essential for that 50-year goal because nobody wants to live somewhere they can hear their neighbors all the time.
Exactly. Noise pollution is a huge driver of resident dissatisfaction. So the wall thickness impacts your unit area, which impacts your building efficiency, all driven by one performance target for sound.
And then you have to layer on time. The schedule milestones. An aggressive 14 weeks from concept to the start of construction.
It's an insane timeline. It's meant to simulate a fast-track design-build project. It forces you to understand that time is money and decisions have to be locked in fast.
Which brings us to the project management question. At which milestone do you have to lock in the location of the major MEP risers?
End of design development, S2. After those first 6 weeks, the core of your building, the stairs, the elevators, and the big vertical shafts for plumbing and power, it has to be fixed, absolutely set in stone.
Because if you try to move one of those shafts later,
it's a disaster. You have to redo structural drawings, engineering drawings, fire-stopping details. It's a hugely expensive disruption that throws your whole schedule off. You have to freeze the scope at critical moments.
And the final piece is communication. The file board itself has really specific rules.
The graphic requirements are there to teach clarity. Neutral background, a 3-column grid, a 100-word summary. But the most important part is the mandatory use of 5 icons.
Egress, daylight, grid, cost, and schedule.
These icons are like a visual checklist. They force the student to prove, graphically, that their design has accounted for the 5 core constraints of the entire project.
If a reviewer can't instantly see the egress path or understand the structural grid, the design is a failure.
It's a failure of communication, which means it's a risky design. Every line has to trace back to a constraint. You're not just making a pretty object, you're building a viable, accountable solution.
So we've covered the technical side. Now we zoom out to the strategic and philosophical context. This is where the curriculum really broadens out into public administration and finance.
And it all starts with the money. So what does this all mean? It means the design has to start and end with a real budget, not just construction costs. And that means understanding the mini pro forma.
This forces students to think like a developer, to understand the total project cost. And they have to break down 12 financial lines, including all the soft costs people usually forget.
We start with costs that exist before you even draw a line. Number one, land acquisition. The cost of the property itself, often the biggest single line item.
Then number two, soft costs. This is architect fees, engineer fees, consultant fees.
Yep. It's a common rookie mistake to underestimate how much it costs just to get the drawings done.
Then permits and fees. After that, we get to the 10 construction cost lines we already talked about.
And then finally, the last two lines that define all the financial risk. Contingency, which we discussed.
And financing carry.
Financing and carry costs. This is critical. This is the interest you're paying on the loan you took out to build the project.
So if your 14-week schedule slips by even a month,
this line item just balloons. It eats away your profit. It forces you to see that time is literally money.
And the test they have to run within this pro forma is brilliant. They have to compare a courtyard scheme versus a bar scheme and show the cost difference specifically in the envelope line item.
This makes them quantify the financial impact of a purely geometric decision. A courtyard has more exterior wall, more corners, maybe a more complex roof, so its envelope cost will likely be higher than a simple bar.
So the student has to prove they can choose the scheme that gives the best performance for the lowest envelope cost. They have to solve for complexity inside that $180 box.
Their design form becomes a financial tool.
And then the curriculum shifts very deliberately to public good and stakeholders, to ethics.
Yeah, this is the big question. How does an architect act in the public interest? And the assignment forces them to consider social impact through 5 ethical prompts.
Prompt 1. Who is displaced or excluded by this typology?
Wow.
Yeah. That forces you to think about gentrification, affordability, your ethical responsibility to the community that's already there.
That is heavy. Prompt 2. How does services like trash and loading affect neighbors?
This is just about being a good neighbor. Is your loading dock blocking the street? Is your garbage attracting pests? Practical, real-world impacts.
Prompt 3. What is the daylight equity across units?
This is a great one. Are you designing a building with a few amazing sun-filled luxury units and a bunch of dark, crummy ones in the back?
There has to be a dignity of access to light and air for everyone in the building.
Prompt 4. Where are the safe routes for kids, elders, and people in wheelchairs? This goes beyond just minimum ADA code.
It's about the whole journey, from the sidewalk to their front door. It's about designing for real human vulnerability.
And the last one, prompt 5. What local workforce or apprenticeships can this enable?
So tying your material choices back to the local economy, could your modular facade be built by a local company? It connects your spec sheet to public policy.
But the hardest part is the equity checkpoint. This is the capstone. You have to document one design move that improves accessibility or affordability without exceeding the $180 cap.
That feels almost impossible. How do you add something good, which usually costs money, while staying under a hard budget cap?
It forces you to make trade-offs. It requires ingenuity.
So an example would be, maybe you make the main corridor wider for better accessibility.
Right, which adds area and cost.
But you pay for it by taking out the expensive granite countertops in all the kitchens and using a cheaper, durable alternative.
The cost savings on the finishes have to pay for the gain in equity.
It forces the ethical move to be part of the financial logic. It proves that good design doesn't have to be expensive design. It just has to be smart design.
And all of this leads to the final lesson, the leadership minute, the philosophical summary.
And the core philosophy is a single statement. Leadership is the choreography of constraints.
That reframes the entire job of an architect. You're not just an artist. You're an orchestrator, a choreographer, managing financial, legal, ethical, and physical constraints.
And the course demands that you transform from being an artist asking for permission, the person who designs something beautiful and then begs for more money, to a builder-statesman earning trust.
You earn that trust by managing risk, by anticipating problems, by encoding the constraints from day one.
It's all about negotiation. They teach you to define what is non-negotiable, safety, dignity, climate performance, versus what is negotiable, like finishes and colors.
And they give you the one ethical phrase you need when the budget gets tight.
What is it?
We can reduce cost here without harming life safety or long-term value.
Wow. That phrase, That sums up the entire program.
It does. It means you protect the core, the structure, the exits, the 50-year performance, but you're willing to be flexible on the things that are less critical. It's about knowing what truly matters.
Ethical leadership isn't about having no constraints. It's about choreographing them into something valuable.
That was an absolutely relentless deep dive into the rigor of the design and build school of KING-KAMBUF. We've seen how they translate abstract ideas partie, proportion into real, regulated, cost-controlled, and ethical architecture.
Yeah, what this shows is that mastery in this field means going from a 10-minute sketch to a fully costed, code-checked plan in a couple of hours. That level of synthesis, where geometry meets finance and law, that's the shortcut to being a truly effective professional.
Every single rule we talked about, the 2.5x daylight rule, the 6 by 6 meter grid, the 2 exits, it was all a test of viability against that $180 per square foot target. You can't separate the art from the budget.
You can't. And in the end, the course asks the students to write down their own personal non-negotiables, the principles they will never compromise on.
Which leaves us with a final thought for you, the listener. If you were starting a big project today, professional or personal, what is your single non-negotiable constraint? What is the core principle you have to build in from day one to guarantee long-term value and ethical performance for the next 50 years?
What's your personal $180 per square foot constraint that defines the integrity of everything you do?
Think about that. We'll see you next time on Beyond the Comfort Zone Talking Shit with KING-KAMBUF.